A great deal of the studying that we do in kinetics has to do with reactions and their rates. Before we can really jump into that, though, we need to consider things that affect reaction rates. And there are four primary things, and you're probably fairly familiar with most of these, although you might not have thought about them much from a particulate or a particle chemistry level. For example, the first factor that affects reaction rates is the concentration of your products, or your reactants rather. So, a couple ways that you can increase the concentration of something before we dive into this. It's easy to think about if you have an acid, and this is a 1 molar solution, that's more less concentrated rather than a 12 molar solution of that acid. It's pretty clear that this 12 molar has 12 moles per liter, whereas this 1 molar only has 1 mole per liter. And if you were to consider dropping a piece of metal in to these acids, since the 12 molar is more concentrated, there are literally more acidic particles in there that will collide with that metal. Therefore, the reaction of it dissolving will happen faster. So, a generalization that we can say is that an increase in concentration will result in an increase in collisions between particles, which will result in an increased rate. The more particles that are present, the more they will collide, so statistically speaking, the faster that reaction is going to progress. But what if it's a gas? Generally, when we're thinking about gases, we don't think of them in terms of molarity, we measure them in terms of pressure. So let's say this container has 8 gas particles in it. If I wanted to increase the pressure of this container, there's 2 ways that I can increase pressure. The first would be to have a container that's the same size, but instead of having 8 particles, maybe this one has 16 particles. By having more particles, I have increased the pressure of this gas, and since there's more particles per area or volume, I have also increased the concentration. A second way to increase the pressure is to maintain that there are 8 particles, but to put those 8 into a smaller container. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Again, you have the same number of particles, but you've compressed them to a higher pressure. Therefore, you've increased the concentration. Therefore, you've increased the collisions. Since there's less space for these to travel, they will collide more frequently. So a good generalization that we can make is an increase in concentration results in more collisions, which will result in a faster reaction rate. The next major factor affecting reaction rates is temperature. And you can think about this one pretty intuitively. If you increase the temperature of a system, of some particles, you're going to increase the velocity of those particles. Because as the equation for kinetic energy, which is temperature, says that kinetic energy is equal to 1/2 times the mass times the velocity squared. So if you increase the temperature, which is kinetic energy, you can't change the mass of the substance, so the only thing you can change is the velocity. By heating up particles, they move faster. Now, since those particles are moving faster, there will be more frequent collisions. Because these gas particles, or any particles for that matter, are simply moving faster, they will collide more often. And since they're moving faster with a larger energy, they will collide more forcefully. And by colliding more forcefully, more of those particles will collide with sufficient energy to overcome the activation energy for that reaction. Okay, so again, an increase in temperature results in an increased velocity of the particles, which means more frequent collisions, which helps the reaction progress faster, and that those collisions are more forceful, so more of them are able to overcome the activation energy, resulting in a faster reaction rate. The third factor affecting rates is the particle size of the particles. For example, if you're trying to, let's say you have a beaker of water and you're trying to dissolve 5 grams of sugar into that water. Well, you have two options. The first is to dissolve a 5-gram sugar cube or to dissolve 5 grams worth of granulated sugar. So just a pile of sugar like you'd pour into your sweet tea. If you drop this sugar cube into the water molecules are going to begin attacking the sugar in order to dissolve it. But they only have access to the outside of that sugar cube. So not as many of the sugar molecules are readily available to do any sort of interaction. Whereas if you sprinkle in this granulated sugar, there's far more sugar exposed, so the sugar will dissolve faster. This is simply just a concept of surface area. If you increase the surface area, generally speaking, you increase the rate of the reaction because more particles are readily available to be collided with other reactant particles. And the last factor affecting reaction rates are catalysts. Now, a catalyst is a substance that provides an alternative pathway with a lower activation energy for a reaction. By providing this alternative pathway for a reaction, this alternative pathway has a lower activation energy than the original reaction itself. And since the catalyzed reaction has a lower activation energy, it is more probable that a collision will be successful whenever two particles collide. Because if you don't have to have as much energy to break bonds, then you'll have just a larger percent of your collisions that are successful. And another important thing to think about with catalysts is that they are not altered during a chemical reaction. Okay, so a catalyst is not altered during a reaction. It's going to be the same chemically as it was at the beginning. So here's an energy diagram showing that. We have this solid line, which I'll color in red, which shows the energy of the reactants. And this large height right here shows the activation energy without the catalyst. Then in blue, I'll go over this dotted line. It's providing an alternative pathway, this catalyst is, and the activation energy with this catalyst is much lower than the red non-catalyzed reaction. So therefore, more collisions will be successful. Another way of thinking about this is a Maxwell-Boltzmann curve. So as you go right, you're increasing in energy. As you go up, you're talking number of particles. If the activation energy is right here along the energy line, whenever you use a catalyst, you're going to reduce that activation energy to a lower standard. And you can tell, let me get rid of this, that here in the red and here in the blue will both represent successful collisions because they're both past the lowered activation energy. Whereas if the activation energy were normal, only the blue would be past that uncatalyzed activation energy. And it's clear to see that there are more particles here than there are just on this part on the right. So there are 4 major things that can affect the rate of a reaction are the concentration of the reactants, the temperature, the surface area, and the use of a catalyst.